All right. Welcome back. I hope you all had a good lunch. And just going to get you folks in here and sit down and be quiet. And then we're getting ready to get Randy to talk about measuring RPKI. That's difficult. Repositories. Thanks.
Randy Bush, IAJ. They have all sorts of warnings on the microphones, et cetera, to be civil and polite, et cetera, as if we normally weren't. Well, you don't have to be with me. Just be honest. Okay, so just in case, I'm an engineer and we always think about the problems. And this is going to be about problems. And I'm a researcher and we're only interested in the problems. The RPKI is actually going real well, except in America. But I want to talk about the problems. Okay, and this was all done by friends. I'm friends with the people at most RIRs who are doing this stuff, et cetera. But I am measuring what they're doing. First of all, if you remember the RPKI infrastructure, there's the certificate hierarchy, et cetera. This stuff's published in a repository. The repositories are gathered up. Yep, wrong button, backwards. Ooh, I can do it. Are gathered up in a cache and then fed to the router. And I'm concerned about the router, of course. And my routing relies upon these repositories. So I'm beginning to worry a lot. And of course, the software that feeds the router, the cache that I control, is, if the people are smart, designed so it's very resilient, keeps, et cetera. But when I look at the current publication hierarchy, it's pretty scary. Okay, there's not much operational quality in it, and this has to be fixed. These graphs are from the open source software we do, and it makes a web page for you. You can look at it. And so here's, for instance, an ISP. And there's how many, I can't even see the slide that I'm pointing to. But anyway, yes, but I can't point there. So how long it takes to fetch the repository from them, how many objects there are, et cetera. And those are fairly reasonable, okay? This is not good. The actual fetching, which you'll see on 3 July, is pretty good. But if you look, you can see certificate errors. So here we have a multi-day outage. And can anybody guess what that was around the early beginning of July? Somebody got it. Jeff wins the prize, the leap second. So anyway, the problem is this RIR doesn't have a NOC. They do not work weekends. And I had to call an engineer inside, and he got it fixed within a few minutes once they knew it was bad. So we're not monitoring this stuff. Okay? Ripe was pretty good. They stayed up across the leap second, but they had continuous fetch failures, which we can look at a little more closely, where we expand this out. And this is, I tried to fetch from them and couldn't fetch, got errors. So what was the problem? We finally got down to it. We were logging it all the time. It was NFS, which is a disgusting protocol and you should never use it. It went on for months. Nothing can be wrong at the RIR. It's fine, it's fine, it's fine. Your measurements are bad. Finally, went around to the back door to the actual ops people and they fixed it. Small problems still remain. So 3 weeks ago, oops, let's see, where's the back button? 3 weeks ago, here was a migration at Ripe, so that's what we expect. Still some errors. So things are a lot better now. But in reality, oh no, I love this one. Here is Afrinic for those folks who actually use Unix, which I hope is most of you. Look at those perms. Aren't they lovely? You don't get to see that very often, right? That's a privilege. Remember it. Okay? By the way, when we wrote to them multiple times, we received snarky responses about how we should have pointed this out to them and who we should have pointed it out to and so on and so forth. Fix it? That's another problem. So, the RIRs are effectively like PTTs. They went to PTC schools. There are no problems, right? So, the software itself has to take care of this. And it does. It uses old data if it can't fetch new, all those wonderful things. So it's fairly stable. And the RPKI data don't change frequently. But you can't run operations, a global operation, with that kind of reliability issue. And if you want to be really scared, remember RIPE's 5-day in-adder outage. And there was a good post-mortem on it. And we're trying to make silk purse out of sow's ears. It's not that the RIRs are sow's ears, but they are our bookkeepers. You don't ask the bookkeeper to run a reliable server. You ask them to keep the books well. Okay? So here's some positives. One positive slide on statistics. This is the number of objects in each repository, and I really want to point out RIPE. That is wonderful. They are now something like 1,500 members have registered objects. Okay? Thank you. That is, no, go back to it. Okay, so the deployment is serious in the RIPE region. It's really good. Alex and Tim are doing a great job. RIRs are not operators. JPNIC is going to try to set an example. We'll see. But the software works around it, and we need more measurement and monitoring. So, where do we go from here? Asking the publishers to provide 5 nines is silly. The Internet's about building a reliable network from unreliable components. So we need to develop protocols and a deployment model based on distributed and cooperative protocols to get service, resilience, and diversity. And we're working on that. So, second half of this talk is, so we've got this RPKI thing that publishes so I can get my stuff in my router, but it's relying on all those publication points, etc. In a large ISP deployment, all these caches will be fetching from the publication points. Okay? We're going to have a laser show too? Come on. Music. Music. So, in this, I'm relying on these publication points, and then I'm pulling them down to caches that I distribute in my network, etc. So what are these caches going to perform like? And what's the reliability there, and what's the what's the propagation time, and what's the propagation time and the deployment? So what are the propagation characteristics of the infrastructure? How sensitive is that to timers? How much is propagation? How much is validation? And what's it like in latency in the network? How does that affect it? So let's remember there's a publication hierarchy, there's the IANA, there's the RIRs, et cetera, and all our wonderful ISPs below them. I just want to point out some players in the game. These are the publication points, which is IANA and the RIRs, et cetera. Then I probably at the top of my tier 1 have some gatherers who fetch directly from those publication points. But I want to keep the load down on them. So I have caches, okay, that feed from the gatherers, not from the publication points, okay? So, and I might have also published my own stuff, and then I've got routers who feed off the caches, okay? So, the cache gets the data from the publication points or other caches. Every cache has the root trust anchor. This is an object security model. So every cache can validate all the data itself. Okay? So somebody lies to it, it's fine. The propagation time is from parent down to child in the hierarchy. And we measure it by having everything log when it receives things. Okay? The architecture is we don't really care about routers in this measurement model because we just care about when the data gets to the routers. We don't care about what they do with it. So we actually use a fake router, which does nothing but receive the data and log. And the caches all also log. And so here's a part of the model. And we have the root, we have the RIRs, we have those gatherers, we have tier 2s, we have tier 3s, etc., all with caches, routers, so on and so forth. Okay? And we have a test bed. The numbers I'll show you will just be from a single tier 1. Each one has 3 gatherers. There are 6 tier 2s for every tier 1, so on and so forth. We actually have a thing with about 1,000 machines, but right now I'm going to show you 300 machines. Okay, 300 caches and routers. And how the heck do you deploy that? You use a cluster, and we're using a cluster that's Japan, I don't know, but it's a research lab up in northern Japan. Cooperates with what Doug Mon was talking about. They've got 1,000 KVMs, by the way, 1,000 big machines. You can't configure 300 servers by hand. So how do we do it? There's something called Autonet Kit. And what we do is we draw literally on your MacBook Air using something called YED, which is a nice graphical thing which produces GraphML. Okay? And you draw this, you produce GraphML, and it actually builds the server configurations, and we deploy them on StarBed, Junisphere, etc. Yes, really. It is automated. Okay? So Autonet Kit originally came from Roma Trey, you know, Lorenzo, who's helped start it down there, Stefano, etc. And then it got hacked in Adelaide University by Matt and Simon Knight, but then taken further at Loughborough University by Ian, Debbie, and Olaf. And the enhancements going on at Loughborough, Autonet Kit as you see it, and has been, by the way, last week, Cisco admitted using it and is going to help provide it to you to replace Dynamips and all that stuff. Address assignment was poor, it needed servers and RPKI knowledge and all that. So we hacked it up seriously. When we wanted delay to test RTT, we actually took the network and we ran the packets from the cache in StarBed to virtual Junisphere routers in Dallas, Texas, and back. And so we could induce 300 to 500 MS delay any point we wanted in the virtual network. And so, hey, when you see the 2 tier 1s here, see this one has dots? That means it went to Dallas and back to get between those 2 points. This is one without RTT, all within StarBed. Okay? And this has delay all over the place. No significant effect. So, we ran fairly large scale. We put the delay, as you saw, both between the publication points and the gatherers, and the gatherers and the caches, and the caches and the routers. No significant effect, RTT. Okay, and it's because things aren't really doing much. Okay, it's just slopping big stuff in big chunks over the network. So the cache deployment architecture you build for a global ISP, don't worry too much about caches in North America getting stuff from Europe or Asia, and vice versa. Okay? So I'm going to talk a little more about the emulation structure and how we allocated things. But we had to artificially talk about what the what the certificate hierarchy was, etc., because we can't generate one. We would love to generate a believable certificate and ROA hierarchy from a BGP table dump. Anybody who can do algorithms to do that, we will buy you a 2 or 3 star dinner. That's a serious prize out there waiting for some computer scientist. I know 3 or 4 people that have already seriously working on that. This is a non-trivial problem. So we did 1 CA and 1 ROA per entity, about 7,500 are added during the run. So what we do is we build this on the laptop, we deploy it on StarBed, it then generates, we hit the start button and it starts generating and distributing the ROAs down to the cache for the existing stuff it was initialized with. And then we start feeding stuff into it 1 per second in real time. So it takes about 2 hours to run to initialize it and upload it to Japan from the UK. It's about 250 megs uploaded and 2 gigs images. We run it in real time, so 1 second equals 1 second. So it runs for about a day, produces about 3 gig of logs, and then about 10, 15 minutes of analysis. Notice, so we assume that we fetch from the RIRs, etc., the publication points once an hour. So ideally, 50% of the samples would have a time of 30 minutes. This is the ideal curve from the publication points to the gatherers. The RPKI router time protocol is negligible, getting it from a cache to the router. Okay, so we initially drop the stuff onto StarBed and then we hit the button and it has to distribute that stuff to the caches. Pardon me, publication point to the gatherers. Okay, this is before we start feeding new data in. So it's not that far off the ideal, has the same slope, no surprise. By the way, this is going to be a no surprise presentation, and we like that. It means the protocols are pretty good. Okay, here it is with steady state flow. Once we shoved the initial load out, now we trickle it out. Notice it's a little closer. I'm flicking back and forth. It's a little better because it doesn't have as big a load to do, and it can trickle them reasonably. Okay, so now we have the data at the gatherers. How long does it take to get to routers? Again, it's not to go back and forth. It's not that different, not that worse, much worse. And then the steady state flow to the routers. It's about the same. Okay, we're trying a BitTorrent protocol, and what this slide demonstrates is BitTorrent is very hard to configure, and we're still trying to work on it, and we did not get a reasonable BitTorrent run before Nanog. Okay, and that is this one, and thanks to StarBed, as I said, DHS, turning your scissors into plowshares. And since I have 11 minutes to go, for free, you get a second, totally different presentation. Pluck the magic twanger, Froggy. Thank you. So, we wondered what the behavior of BGP was like on the wire. Okay? And we're going to wonder for a long time. Not working. There we go. So, of course, the goals, thank you. The goal is to, of course, make BGP convergence faster. So, here's the measurement we did. We took and we wanted to shine some light on the subject. 2 ASR1Ks on a wire with a mirroring switch between. So this is just a LAN with a switch. TCP mirrored the switch off to a server with TCP dumping. Saving the dump, we hit reset on the BGP session, we measured the BGP session. Pretty simple stuff. Here's time sequence plots. Uh-oh, you're showing the PDF, not the PowerPoint. So we're going to have this all on one slide. Sorry. For those people who don't remember TCP 101, and to tell you the truth, I hadn't played in this field for 18 years, and so I had fun relearning a lot of stuff. Here is a segment being sent, bunch of packets. This is the segment counter, how many bytes you are into it. Here, the ACK comes back, next segment sent. Okay, so this is the RTT, not of the wire, but of the TCP session. Send it, got the ACK. Okay, this is the advertised window, how the receiver says how many bytes I can swallow in one chunk, and the sender says, here's what I can do. This is known as the congestion window. Okay, so warning, the pictures you're going to see, the tool I use, the scale's a little arbitrary, and so don't read too much into what you visually see the numbers. Here is, we're seeing the congestion window is being stuffed by the advertised window. So the advertised window is limiting how much can be sent. So that's saying the receiver is choking how much can be sent at any one time. We'll get numbers shortly. So the RTT, we focused immediately. Here we are on a wire, and we have the 75th percentile being 116 milliseconds. RTT on a wire. Not good. So, this is the dog we chased. So, this is the RTT over the full session. So we wanted to see, and we had the BGP and stack implementers working. I mean, Cisco is working on this with us. In fact, they initiated the project. I mean, there are a number of you sitting out there with BGP sessions with a million plus routes in it for VPNs, et cetera. So we want that stuff faster. So Cisco's working hard on this. So you're seeing just a work in progress, by the way. Okay? So we see, ooh, there's one ACK for an entire window. This is known as stretch ACK. Could this be the problem? So there's also occasionally a loss and a retransmit, but not often. Okay, so is stretch ACK the problem? It could lead to the RTTs. It could make things bursty, and it could cause us, the burst could be overwhelming a transmit buffer. There's also the small advertised window. Due to constraints in antique routers, the actual buffers are small. So 32K is all you get for an advertised, for a buffer, so that's the advertised window. And what you'd really like is the bandwidth delay product, but that's life in the big city. So we increased the advertised window size, no win. Okay, not the problem. I mean, we got a little win, but no real big win. We removed the stretch ACK, still 115 mils. Okay? RTT is still high. We drop, okay, Cisco iOS, which is XE, doesn't have a real tasking model. It does what embedded systems do, which has run to completion. There's a task queue, and I keep running, but I promise to check within n milliseconds, and if that timer's up, I relinquish and put myself on the task, on the to be resumed queue. Okay, so it's all voluntary. The RTC normally is 50 milliseconds. We dropped it to 25 and cut the RTT in half. So you say, wow, a real tasking system like Linux is going to make this all wonderful. Ha ha ha. There's a dirty trick. You get an attack from layer 9. The layer 9 attack is a router vendor is implementing this stuff, and they don't, the Linux kernel has the GPL poison. So I can't put my critical code in the kernel. So I have to swap out to user space. And guess what that costs? We haven't seriously measured, but the last slide will show you an alarm there that says, same problem there. So RTC is something you can tune. By the way, observe that little right there, and you can go set that. You can get it as low as 20 and really cut your RTCs, your RTT on your ACK. Okay, what if it's the TCP stack? What if there's a 6 stack? These stacks haven't been seriously hacked in 10 years. So let's measure a non-BGP protocol. Now remember, routers can do the RPKI router protocol, which is this nice, slick TCP protocol. There we see it. It's beautiful. This is the servers in Dallas. The client is in Seattle. We see a 78 millisecond RTT. That's all due to distance. And look at them. Nice big windows opening up, chunking along. I mean, the window size is still limited, but because of buffering, but that's the way you want to see TCP. So the stack looks good. Okay, it really looks good. So the window's a little small, but that's life in the big city, right? Or in the little router, right? They're still saving RAM in 2012. So is it BGP or could it be rib to fib? Remember that problem. So we take it and we reset the receiving BGP receiver has a policy statement that just drops the BGP announcement on the floor instead of doing best path and stuffing it in the fib. 50% savings. So 50% of your dollars are being spent still, 15 years after the first research showed this was a problem, still moving stuff down this thin little straw to the fib. Okay, so the two big problems so far we can hit is run to completion timer, rib to fib. We can get rid of the stretch hack, doesn't do a lot. Open the window, better. Okay, we have two big opportunities. So we really want, this is XE, we really want to measure XR. During the experiment, we actually accidentally measured XR because I wanted to see, when I was measuring the RPKI protocol from Seattle to Dallas, I said, hey, I've got an XR machine in Dallas right next to the server. Let's try that. What we got was something very strange. Fast RTT, but the window size was only one segment. That's scary. So something is wrong in there, in stack, etc. We will play with it. We will find out. And I still have 2 minutes remaining, and I don't have another presentation to fit into that small a slot. Cheers. Come on.
No questions for Randy?
No.
No. Okay.
Howard.
Get off.